So I'm starting straight with the introduction. And well, what I would say as an introduction is that in oil provinces there are plenty of wells for sure, but to find a good determination of heat flow is another problem. So heat flow, oil industry claims, is a very important parameter for us. Well, here we have an example. This is basically the mid-Norwegian margin. Norway, oops, that doesn't work. Ah, yes. Yeah, Norway is here, Barents Sea, the Norwegian Sea here. And basically what you see here is a nice heat flow map, but most of the entries are actually marine heat flow data, which are not especially bad, but they are, as you see, restricted in deep waters or even in oceanic crust, leaving whitish big parts of the margin where actually the oil wells or the oil exploitations are based. We find a few shallow wells with a few determinations. In some places we might find, so this is actually further south, the city of Bergen is here, this is the North Sea. In some places you might find some determination from oil wells, but this is really seldom normally. So the situation when I started this study was the following one. Heat flow determinations from deep exploration drill holes have been published, but they are very scarce to start with. And when they are published, very often you don't get access actually to the primary data. So it's very difficult actually to have an idea about the quality of the data. Marine heat flow do exist for a long time in that region, but unfortunately, as I said, they are restricted to deep waters. So we have actually a gap. And another problem, which is a typical problem with heat flow data, I think, is that comparison of data gathered with different techniques is not always so seldom. So what we wanted to do here is try to start a new heat flow study using as much as possible the information from the oil exploration wells and to have something uniform. Okay, so what is the problem? Well, the problem is very, very simple. The way I formalized the problem at the beginning, I told myself, well, I can actually get a heat flow determination if I have two temperatures, of course, if I know the vertical distance separating the two measurement points. Okay, so this was quite easy to get. One temperature is, of course, the surface temperature that, well, we don't have, but we can estimate quite easily, normally. And another temperature might be one temperature measured in the well, a good one, preferentially. So this okay, and the distance, of course, is the depth to the measurement point in the well. We can do it. Okay, basically that's what you find in most databases. The problem, of course, now is to get this terrible parameter, which is thermal conductivity, that you know all depends on porosity, on temperature, and on rock matrix lithology. Well, in my case, I was fortunate that porosity, I can get it. Just using the Sclater and Christie's laws that were published in 1980, it turns out that these laws were actually based on data from the North Sea itself. So it was a perfect let's say, approximation for me. Then I found out that in petroleum reports, we may find a fine description of drill cuttings. Let's say that cores are very seldom, but actually a description of the lithologies penetrated in the well are quite let's say, general, obvious, actually, to find. So I could get out from that the matrix lithology of the rocks. Okay, once I got that, I use actually the thermal conductivities of the matrix published by Brigot et al. And then I could actually reconstruct that, and then, oops, potentially calculate heat flow from oil petroleum oil wells in the North Sea. Okay, just to show you the database we use. So we had an entry of 1,400 wells. What we wanted to, well, you cannot read all that, but it doesn't matter very much here. What I wanted to show, well, this is the name of the well and a lot of information, but I want to show that we had to do a quite severe sorting of the data, and out of these 1,400 wells, we just retained 63 wells that could be a workout. Why 63? Because we wanted to have both a good description of the lithology, so precise description, all along the well, down to the depth of measurement of the temperature. And second, we wanted to have drill stem test temperatures, not bottom hole temperatures, because the quality of bottom hole temperatures is very, very difficult to estimate, at least from the reports from industry themselves. Okay, so we sorted out all this data. So we have data, we have an idea. Then it's just a question to write a numerical routine to calculate heat flow. Well, we needed to solve the problem in a numerical way simply because temperature depends on conductivity and conductivity depends on temperature. So we needed this kind of routine. Well, in one word, what we did here is that actually is to break down the length of the well in small intervals, such as porosity and temperature are the variation of both parameters is negligible, and we can estimate for each interval the conductivity. And then it's just a question to select a heat flow value and to cascade the calculation of temperatures. If the bottom temperature corresponds to the measured temperature, we have a solution. If not, we restart. Okay. So basically, this is what we get as input and output from this exercise. So input, the temperature in the well for sure, the lithology, of course, that we need for matrix conductivity, the porosity that depends both on depth and lithology. And then we can calculate the in situ conductivities here, the temperature profile, the temperature gradient, and here in small is actually the estimation of heat flow for that well that comes from the North Sea, and some Monte Carlo simulations to see the stability of the result. Okay, so I think I pass to the following. Yes. So these are the results from the 63 wells, well, basically from the southern part of the Norwegian North Sea here up to the Barents Sea. Well, I will come back later on details here. You can remark that we got values between something like 50 to 80 milliwatts per square meter. Added to that map, actually, this is something I will use later on. I added some marine heat flow data in deep water simply because there are no wells there. So if I wanted to build something that looks like, let's say, a heat flow map, I needed to pick up data from other places. Okay, so on one plot, all our determinations. Blue is the North Sea. We got something which is relatively, well, stable, I would say, with some variations, but still okay. There is no trend with depth, at least in the North Sea. This is the value we got, about 65 milliwatts per square meter. The same value for the mid-Norway Sea, the mid-Norwegian shelf, here in red, and 65 again. The Barents Sea, we got higher values, 72, and some kind of trend, but not really well defined because we were limited in the number of wells we could at least calculate here. What we did as well is, of course, the things are not so simple. We tried to estimate the perturbation by quaternary sedimentation erosion, which is not an easy task, I would say. But at least we got some numbers. We have, let's say, some uncertainties concerning those values here. that range from 4 to 10 milliwatts per square meter. This is what we got. Okay, so these are the final maps we produce from this study. So the Barents Sea is here. You can see Norway, I think, Scandinavia, the North Sea, and the mid-Norwegian margin. Okay, and again, I repeat, I combine with those data that are marine heat flow data here. Okay, interpretation. We see our data, our results at least, indicate that we have an increase in heat flow from east to west in the Barents Sea. This was relatively easy to interpret for us. It was really the clear sign that the lithosphere is thinning from east, so the cratonic Barents Sea, to west, the young Atlantic Ocean, Northwest Atlantic Ocean, here in the west. So this was our interpretation. Then we had other features that we tried to interpret, well, thanks to other independent data. For example, we could, we had that result that heat flow is increasing from, let's say, this part of the North Sea, going actually to the Norwegian margin, basically. We are going to say that. And the interpretation we had, especially taking this tomographic model here, is that we were moving from a thicker lithosphere to a lithosphere that was thinner and thinner progressively to the north. That was our interpretation, so we think that it's a deep signal in that case. Perhaps interesting as well was to note, we don't think that it has something to do with changing actually the type of data, but to note that we had a serious decrease in heat flow when we are moving towards these two areas that are the very deep Møre and Vøring basin. Our interpretation was that what happens there, and this we are sure of it because we have the seismic data, what happens there is that the reduction in the thickness of the upper crust is such as that we have a severe reduction in the heat-producing elements from the crust. That explains why we have this drop in heat flow. Okay, so this is my summary. Well, these are, perhaps I don't repeat the numbers again, but these are the numbers we got, which basically I think makes sense in this kind of context, in tectonic context. Yes, again, I don't repeat that, but perhaps I will point out something that we have only considered 63 drill holes, and it's a pity. We can do much better if we get better data than what is actually reported publicly by the Norwegian Petroleum Directorate. Okay, thank you very much for your attention.